Hello, everyone. My name is Victor Surowski. I'm a master's student here at the University of Michigan Dearborn studying robotics engineering. Today, I'll be talking about the bidirectional encoder representation from transformers, or BERT. The motivation behind the BERT model was to improve upon previous language representation models by better capturing the contextual relationships between words in natural language text. Previous language models, such as word embeddings, treated each word in a sentence as an independent unit and did not consider the relationships between words in that sentence. BERT, on the other hand, is a pre-trained language model that uses a deep bidirectional transformer architecture to consider the entire context of a word by looking both forward and backwards in a single sentence. This approach allows BERT to better capture the nuances and subtleties of natural language, such as understanding the meaning of a word based on the context in which it appears. BERT has been shown to outperform previous language models on a variety of NLP, natural language processing tasks, including question answering, sentiment analysis, and name entity recognition. The BERT model was a major breakthrough in NLP when it was first introduced by the Google AI Language Group in 2018, officially published in 2019, early 2019. It was the first model to demonstrate the power of pre-training a deep neural network on a large corpus of text using a self-supervised approach, which allowed the model to learn a rich contextual awareness of word representations that could be later fine-tuned for various downstream tasks. There have been several related works to the BERT model. Some of these include ELMO, the embedding from language models, which was introduced by researchers at the Allen Institute for AI in 2018. This is a large language model which also uses a bidirectional long short-term memory, or LSTM architecture, to produce embeddings for words that are sensitive to the context in which they appear. Additionally, the GPT family of language models, the generative pre-trained transformers, which were introduced by the OpenAI teams initially in 2018, use a transformer architecture to pre-train a language model on large amounts of data, which can also be later fine-tuned for specific NLP tasks. The next two, the Transformer XL model, is a language model introduced by Carnegie Mellon researchers in 2019. It uses a transformer architecture and a segment-level recurrence mechanism to capture long-term dependencies in text. And finally, the second iteration of the BERT model, Roberta, was trained with a larger batch size, more data, and longer sequences, and this has been shown to lead to improved performance on a variety of NLP tasks that the initial BERT model seemed to struggle on. Despite the successes of these newer models, BERT remains an important and influential model in the field of natural language processing. Its innovative pre-training methodology, model architecture, and its success inspired future research and development in the field. In summary, while BERT may no longer be the state-of-the-art model for many downstream NLP tasks, its impact in the field cannot be understated. Its approach to pre-training large language models has opened up new avenues for research and development in the NLP processing, and it's continued to be an important research point for future advancements in the field. The BERT model is a pre-trained model using a combination of two unsupervised learning tasks. First, mass language modeling, and second, next sentence predictions. During pre-training, BERT is fed a large amount of text, such as Wikipedia or the book corpus dataset. The text is then tokenized into subwords using the word piece algorithm, which allows the model to hand out of vocabulary words and reduces the overall vocab size. BERT is then trained using two primary objectives, mass language modeling and next sentence prediction. This model uses a transformer-based architecture with 12 or 24 layers, depending on the specific version of the model you're using. Transformers are self-attention-based neural networks that can learn to attend to different parts of the input sequence to extract relevant information. During the training, BERT is optimized using the stochastic gradient descent with Atom Optimizer. Once pre-trained, the model can later be fine-tuned on specific NLP tasks by training on a smaller subset of task-specific datasets. Overall, the training methodology of BERT is designed to allow the model to learn powerful representations of natural language that can then be adapted to a wider range of downstream tasks. By pre-training the model on a large and diverse corpus of text, using only two primary objectives, mass language modeling and next sentence prediction, BERT has been able to learn to capture the complex relationships between words and sentences that are essential for understanding natural language. In the next few slides, I'll provide further details in regards to the training data, training methodologies, and the attention mechanism. So to start with the training data, or in the field of natural language processing, the corpus selection. To train a pre-trained language model, such as BERT, we need a large and diverse corpus of text. The BERT model was trained on a combination of two corpora, the Wikipedia and book corpus datasets. As we all know, Wikipedia is a vast online encyclopedia that contains millions of articles on a range of topics, making it the ideal source for diverse text. The book dataset, on the other hand, contains over 11,000 books from a variety of genres, including fiction, nonfiction, and children's books. When combining these two corpora together, it's provided BERT with a broad range of language use cases. After we've collected our data, we need to tokenize it from natural language into fragments or embeddings that the model can understand. So before BERT can be trained on the text must be tokenized into smaller units of meaning. BERT uses something called the word piece algorithm, which breaks down the word into smaller subwords. This allows the model to handle out-of-vocabulary words, which reduces the overall vocabulary size. For example, the word unbelievable could be broken down into words such as on, believe, and able. The word piece algorithm used by BERT to tokenize text into subwords adds robustness in a few different ways. First, it allows the model to handle OOV or out-of-vocab words, which may not be included in the predefined vocabulary used by the model. OOV words can be a problem for many NLP tasks and models because their occurrence of frequency is different for different text or domains. By breaking down words into subwords, BERT is able to still recognize and process these out-of-vocab words that share common subword meanings with known words from the model's vocabulary. This allows BERT to capture a more nuanced relationship between words and their context, which can improve the model's performance on downstream tasks. Finally, the model also uses these subwords can help us handle variations in spellings or morphology of these words. For example, by breaking down the word unbelievable into subwords on, believe, and able, the model may also be able to recognize related words such as believe, believably, or unbelievably. Overall, the use of subwords in BERT's tokenization process adds robustness to the model by allowing it to handle a wider range of words and variations in spelling morphologies, while also reducing the vocabulary size, which improves the training efficiency of the model. So, to train the model, a certain percentage of these input tokens will first be randomly selected and replaced with a special mask token. The model is then trained to predict the original token based on the context of the other tokens in the sentence. This task is called masked language modeling, and it's a form of unsupervised learning. It forces the model to learn a bidirectional representation of the input sentence, as it must consider the preceding and succeeding words in order to predict the masked token. MLM, or masked language modeling tasks, used in BERT's training process adds robustness in a few ways. First, it allows the model to learn from unannotated data without the explicit need of human supervision. Second, by randomly masking tokens in the model must learn to recognize and generate missing words based on context provided from its surroundings. Overall, the masked language modeling task used in BERT's training process adds robustness to the model by allowing it to learn from unannotated data, improving its ability to generalize to new text, and helping it capture more important contextual information and long-range dependencies in the text. After the model has been able to predict these next word predictions, the model then goes through a training step called next sentence prediction. In this task, a pair of sentences are presented to the model, and it's trained to predict whether the second sentence follows the first sentence in the original text. This task helps the model to understand the relationship between sentences and the context in which they appear. However, in later papers, such as Roberta, the authors found that next sentence prediction used in BERT's pre-training did not provide significant benefits for the model's performance due to the vast size of the corpus training data. For smaller models, the authors suggest that if you have a limited data source, next sentence prediction could be beneficial. However, for large language models such as BERT, this did not add a significant benefit and only further increased the training time. The BERT architecture is based on a transformer neural network, which employs the self-attention mechanism to capture long-term dependencies in natural language text. In this type of deep learning, each element of the input sequence is attended to by all other elements in that same sequence to compute a weighted sum that captures the relevance of each element to the task at hand. To achieve this, we use three input vectors: the query, the key, and value. With the query vector, we use this to compute the score for each key vector based on the similarity of the two, which is then used to compute the weighted sum for our value vectors. We're able to stack multiple attention layers on top of one another to form the transformer neural network, which is designed to process sequential data efficiently. The self-attention mechanism has several advantages over a traditional neural network, including its ability to capture long-range dependencies between sequence elements, the ability to parallelize computation across multiple sequences, and its ability to process sequences of varying length. In the case of BERT, the self-attention mechanism is used to capture the complex relationships between words and sentences. This is essential for understanding natural language. Additionally, this results in a bidirectional understanding of the input sentence, allowing BERT to adapt to a wider range of downstream tasks with high accuracy. The use of the transformer architecture and the self-attention mechanism in BERT has thus been revolutionized in NLP and led to the development of even more powerful language models, such as RoBERTa and the GPT architecture family. Excuse me. The training methodology of BERT has had a significant impact in the development of large language models in general. BERT's approach to pre-training and fine-tuning the model has become a standard in the field, and many subsequent models have followed a similar methodology. One of the key contributions of BERT is its use of the pre-training objectives that encourage the model to learn a deep, bidirectional understanding of language. By pre-training on a diverse corpus of text, both mass language modeling and next sentence prediction by using diverse text and the pre-training objectives of mass language modeling and next sentence predictions. In addition, BERT's use of transformer-based architecture has become a standard in the field. Transformers have been shown to be highly effective at modeling natural language and have been used in many subsequent models, most notably the GPT and GPT-4 families. Overall, the training methodology of BERT has set a new standard for the development of large language models. By focusing on pre-training objectives, model architecture, and fine-tuning processes, BERT has demonstrated that it is possible to develop and capture the complex nuances of natural language tasks. As a result, the influence of BERT can be seen in many, many subsequent models, and its impact on the field of NLP is likely to continue for many years to come. BERT has shown impressive performance on two major natural language understanding tasks. It achieved state-of-the-art performance on the GLUE benchmark, which includes 9 diverse tasks such as sentiment analysis, natural language inference, and sentiment analysis, natural language inference, and language understanding. Additionally, the BERT architecture achieved state-of-the-art performance on the SQUAD Stanford question answering dataset, specifically the second version of this dataset, which is a challenging task that requires the model to not only provide the correct information, but identify when the information is not present or the answer is not present to the question in the given context. These results demonstrate the effectiveness of the BERT model at handling various natural language understanding text, and it's led to the widespread adoption of the BERT pre-training architecture in the field of NLP. In conclusion, the BERT architectures or the BERT model's representation of natural language has provided a significant breakthrough in the NLP field. Its innovative pre-training methodology, model architecture, and fine-tuning process have demonstrated the power of deep bidirectional language learning for capturing the complex relationships between words and sentences in natural language. The novelty of BERT lies in its pre-training a deep bidirectional transformer on a large amount of text, enabling it to learn a rich representation of language that can be adapted to a wide range of downstream tasks. By combining both mass language modeling and next sentence prediction objectives, BERT can capture both the local and global context in natural language. The experimental results of BERT have shown that it achieves state-of-the-art performance on a wide range of natural language tasks, including sentiment analysis, name entity recognition, and text classification. Its success has inspired future research in the field and set a new standard in the development of large language models. Overall, the BERT model represents a significant advancement in the natural language processing and has laid the groundwork for the development of more sophisticated models. I would like to thank you all for listening to my presentation on the BERT model and its performance on natural language processing tasks. I hope that you found this information informative and valuable. As we continue to advance in the field of NLP, models like BERT will continue to pave the way for even more sophisticated approaches as we go forward into developing large language architectures. I would like to thank you again for your attention and interest. My name is Victor Sirowski, and I look forward to hearing your feedback. Thank you.